All right, so we finished grading your midterm one as we promised. I posted your grade earlier today. So our class average is 81.7. I'm very happy with it, by the way. Last quarter, my average is about 70. So I'm very happy, and I hope you're also happy. So you can check your own grade on Gradescope. The regrade period will be open until the end of Thursday. So you have 3 days to submit any regrade request that you want on Gradescope only, right? So we don't take regrade policy. We do not take regrade requests through email. So please submit anything you want to do over Gradescope. We'll see it. We'll update your grade whenever we see fit. But keep in mind, a regrade request can work for you or against you. Basically, whenever you submit a regrade request, we just look at that question again and reevaluate it. It can work for you or against you. And I posted a key to your midterm exam. It's in the module. It's my handwritten key, so it's a little bit hard to read. I apologize for that. On one of the questions, I made some ambiguity. So that's the expansion into vacuum question. So I have a side note there. So there are two sets of questions that are both correct. So all 0 is correct. The other one is the right one if you're using that's just not very good question. So I add a side note saying like two sets of answers are both considered correct because of my mistake. Okay, and if your exam does not scan well on Gradescope, like if you write down something on your physical exam, just a scanner didn't catch it, come to my office hour and actually find your physical exam. We'll grade your physical copy of the exam just to make sure we have that correct. And if you haven't done so, the survey is available. It gives you extra credit, and tell us what you feel. Feel free to go back and update the question about how midterm 1 feels to you after you see your grade. I'm fine with it. Like, really, tell me the truth. And I read them, and I want to improve based on your feedback. All right. Any questions before we move on into materials? No, we're happy? Okay, sounds good. All right. So today, it's what? I want to say this ahead of time. This is my favorite lecture because this lecture is connecting the dots that we did in everything before today. All right, so this lecture is called Thermodynamic Relations in Equilibrium Systems. So now considering a system at equilibrium, we're talking about the relationship between all kinds of state functions that we discussed in the previous lectures. So we'll start from 6 basic equations. And from these 6 basic equations, we will derive a set of Gibbs equations and then a set of Maxwell relations. And then using the Gibbs equations as Maxwell relations to provide general solution to say, like, what is the dependency of, say, temperature and volume of internal energy? What's the dependency of temperature and pressure for enthalpy, etc. So today will be the lecture of connecting all the dots that we discussed before. All right. So before we do that, let's just review the set of basic equations we went over. So if you're creating a like equation sheet, these 6 equations should definitely be there. I'm just going to rewrite them on the board so that later on I'm also going to add more and more equations that's derived from these basic equations on the board with you. So when we say these are basic equations, let's look at the first one. In the first equation, that contains both our first law of thermodynamics and second law of thermodynamics. And how do we do that? So it reads du equals to TdS minus PdV in a closed system, reversible processes, PV work only. Or we can consider that's a system at equilibrium. All right, so when the system is at equilibrium, we're using both our first law and second law of thermodynamics. Our first law of thermodynamics states my du equals to dq plus dw. That's our first law, right? So first law. And then in my second law, we have my dq reversible over t equals to ds. That's our alternatively, you can write dq reversible equals to TdS. And for our work reversible, we have dW equals negative TdV. And that's where that first equation comes from. So that du equals to TdS minus PdV takes consideration of both your first and second law of thermodynamics. So far, so good. Should be a quick review. All right, so I'm going to remove these derivations here. And by the way, let's use first and second law. And then we have a bunch of definitions. So the following state functions are defined based on their relationship or their relative relationship with internal energy or entropy. So in this case, we have enthalpy is defined as U plus PV. So whenever we write something like this one, this is by definition. All right, so in any cases, your enthalpy is defined to be internal energy plus PV. Just how we define that. Likewise, in our last lecture, we define our Helmholtz energy A equals to U minus Ts, and G equals to H minus Ts. All right, so we define these two new state functions in our last lecture so that we can describe material equilibrium at constant Tv and constant Tp conditions. All right, so we define these state functions. These three equations are by definition true. All right. And next up, we have our heat capacities. We have our Cv, which is partial differential of U over T at constant V. Cp equals to dH over dt at constant P. And these use this condition here as well. So closed system, equilibrium, PV work. So these are our 6 fundamental equations. We'll come back and revisit them in our later sections, but here's a quick review in what they are. All right. So first step, let's think about what else do we know about Cv and Cp at equilibrium conditions and see if we can find alternative expressions for my Cv and Cp at equilibrium conditions. And can people see my writing on the board? Okay, sounds good. Yeah, sometimes I tend to write like very small on the board, so if you can't see it, do raise your hand. And also for anything on today's lecture, raise your hand whenever you think like, oh, I can't follow, or I don't know what she's doing. All right, so I don't want this one to be a confusing one, because it's very easy to get confusing, like today's lecture. So first of all, we're trying to focus on my Cv and Cp to find an alternative expression for these heat capacities. So recall our original definition of these heat capacities. We're saying a heat capacity C with a subscription X, so X is that variable which held constant for that heat capacity, equals to dqx over dt. And since we're looking at equilibrium conditions, we have ds equals to dq reversible over t, or at constant x and equilibrium, we have Cx equals to TdS over dt. Right, so this is my ds, TdS equals to dq reversible. So my Cx becomes TdS over dt. So now, if we're replacing that Cv and Cp with this new expression, what we end up getting is Cv equals to temperature times ds over dt at constant V, and Cp equals to temperature times ds over dt at constant P. Just alternative way of writing my heat capacities. I'm just going to add it up to 0. Okay, so the heat capacity part is, let's leave it for now. That's just alternative way of writing it. So like when you see this kind of expression that's telling you that's an alternative expression of heat capacities. Okay, that's goal number 1, checked. Straightforward. Goal number 2, derive what we call Gibbs equation from the basic equations. Or what we're trying to do here is for these closed reversible processes at equilibrium, PV work only, can you express your du, dH, dA, and ds in the same format as my du equals to TdS minus PdV? All right, so in this part, the thing we're using, the calculus we're using is very straightforward. We're using my dx plus y equals to dx plus dy, also dxy equals to x dy plus y dx. Right, so from here, we're rewriting my dH, dA, and dg in the form of the du equals to TdS minus PdV. How do we do that? Well, firstly, we write dH. Now, we can always replace that enthalpy with its definition. Right? So what's the definition of enthalpy? U plus PV. So we can always write that as U plus PV. This is just by definition, H equals to U plus PV, so we can do it. And then using these two equations in basic calculus, we can rewrite dH equals to du plus PdV plus VdP. So far, so good? And then, well, we know what du is in that expression. That's using my first law and second law. We know that du equals to TdS minus PdV. All right, so plugging u to my equation, we end up getting dH equals to, well, my PdV and PdV cancel out. So my dH equals to TdS plus VdP. So I'm just going to add it there as part of my Gibbs equation. So we have dH equals to TdS plus VdP. Only coming from our first du equals TdS minus PdV and using the definition of enthalpy and our basic calculus. We can do the same for the rest of the equations like A and G. So let's just do that together. So we have dA by definition equals to du minus Ts. Right, so same thing. We have du minus TdS minus SDT. My du equals to TdS minus PdV. Now TdS cancel out. My dA equals to negative PdV minus SDT. All right, same applies to delta G. We have dG equals to dH minus Ts, and that write out to be dH minus TdS minus SDT, and that gives you, well, my dH equals to TdS plus VdP minus TdS minus SDT. Right, so my TdS cancel out, so my dG equals to VdP minus SDT. Right. So this part is the derivation of a set of equations called the Gibbs equations. All right, so these four equations together are called Gibbs equations. And then these 6 equations together are my basic equations. Call them basic 6, so definitions. So the Gibbs equations were derived from the basic equations. So now thinking about our Gibbs equation, what we end up getting. What we end up getting here is that, for example, internal energy is a function of variable S and V, right? Likewise, your enthalpy is a function of S and P. So from here, from our Gibbs equations, we can start to take one step further of writing out the total differential and think about what exactly are these state functions in front of my differential. All right, so in the total differential equation, that's going back to all the way at the beginning when we talk about calculus. Remember, if you have a function, let's say a random function z as a function of x and y, the total differential of z, we can write it out as the partial differential of z over x at constant y dy plus dz over dy at constant x dy. This one should be x, thank you, sorry. All right, so that's just writing out the total differential of a random function with 2 variables. So in our case, we have u, h, a, and g. You can write that as the same way to write out the total differential equations of my u, h, a, and g and find out some very interesting expression. So what about this? Let's do it together. What is the total differential of u as a function of s and v? So doing the same, writing my total differential as partial differential of u over s at constant v ds plus partial differential of u over v at constant s dv. All right, so this one is just calculus. We know u is a function of entropy and volume and writing out the total differential. At the same time, using thermodynamics or the Gibbs equation, we have du equals to TdS minus PdV. So what do we end up getting? We get this one, my partial differential of u over s at constant v equals to temperature, and this one, the partial differential of u over v at constant s equals to negative p. All right. Or the other way to put it is when we're thinking about temperature. Yes, in previous cases, we already talked about temperature being a measurement of telling us whether or not 2 systems are at equilibrium with each other and they're at thermal equilibrium with a third system, right? So now if we think about deeper, like what is temperature? Temperature tells us how does your internal energy change with respect to entropy at constant volume. All right. So this part is like a bunch of operation, and it's like, okay, so now we have ways to express temperature as partial differential equations of internal energy with respect to entropy, and pressure as a partial differential of internal energy of volume and at constant entropy. So these are the relationship that comes from my Gibbs equation. So these partial differential comes, we have du over ds at constant v equals to t, du over dv at constant s equals to negative p. So let's do the same for the rest of the Gibbs function and see what we end up getting. All right, so starting from dh, we know that enthalpy, reading it, it's a function of entropy and pressure, right? So dH as a function of entropy and pressure you can write its total differential as partial differential of enthalpy over entropy at constant pressure, ds, plus dH over dP at constant S, dP. And our Gibbs equation, we have dH equals to TdS plus VdP. And what we end up getting is my volume is my dH over dP at constant S. My dH over ds at constant P is my temperature. All right. So why don't you try derive the same thing for A and G? I'm going to write it on my iPad at the same time while you're writing, so we can check our answer later on. Right. Are we getting the same thing? All right. And a few things here, you can think about it as like, okay, so it actually matches our expectation. So we can do a quick sanity check. Like, for example, if we're taking du over ds at constant v, so we have an extensive function over an extensive function, we're getting an intensive function, right? Likewise, if we're taking dA, which is extensive, temperature is intensive, we're getting S as our extensive function. So quick sanity check to make sure you get the same result. So these are sets of partial differential equations that's linking something of a thermodynamic property with respect to a partial differential equations. But still, at this moment, we're wondering like, okay, it's easy for us to measure volume. It's easy for us to measure temperature. It's not so straightforward for us to measure entropy, right? So why do we care about it? Like how, I mean, we can never have a thermometer that tells us, hey, what's the entropy of the system? So here comes to the power of thermodynamics. So from here, we'll then use one more calculus tool so that we can translate difficult to measure thermodynamic state functions like entropy, Helmholtz energy, Gibbs free energy, or enthalpy into terms that we can measure experimentally. So what are the terms we can measure experimentally? Well, you can think about alpha, which is our thermal expansivity, which is 1 over V, dV over dt at constant P. We have chi, which is 1 over negative 1 over V, dV over dP at constant T. That's our isothermal compressibility. we have our joy coefficient. So mu j equals to dt over dv at constant internal energy. Mu jt equals to dt over dp at constant enthalpy. Like these are the things you can experimentally measure, right? So the next question becomes, well, how do we connect them? How do we connect these partial differential equations you can experimentally measure into some of these partial differential equations that we don't know how to deal with them? So that we will use one more calculus tools, or one more calculus trick, which is the Euler's reciprocity relations. So looking at it together, what is Euler's reciprocity relation? Okay, so raise your hand if you have learned this before. Never heard of it? Okay, I'm gonna go very slow here. So in this case, we're just using calculus, nothing fancy, right? So the basic calculus we're using is two things. One is this partial differential, the total differential of a equation, like z is a function of x and y. As we were saying, you can write this as a partial differential times dx, right? So the dz xy, you should be very familiar writing this. We have dz as a function of dz over dx at constant y, dx plus dz over dy at constant x dy. Right? Just writing out the total differential of a function z with two variables x and y. And now in here, let's just say I call this first partial differential dz over dx at constant y as big M. And then I call the second term, which is dz over dy at constant x, as my big N. So I'm just giving them a name so that it's easier to follow. This is basically what we did to get these partial differentials from the Gibbs equation. And now what we have is dz equals m dx plus n dy. All right? And then using one more calculus rule, that is the order of partial differential equation doesn't matter. So you can choose to take this partial differential with x first, or you can choose to take this partial differential with y first. So this is also what we did before when we talked about calculus. When you're taking when you're taking two differentials, it doesn't matter which one you take it first. You always get the same answer. We did that practice example together of if you take it over x first or over y first, will always give you the same answer. And now let's think about it. In here, this dz over dx at constant y, we are calling it m, right? So that's our big M. And this dz over dy at constant x, that's our big N. So by using this fact that the order of the partial differentials doesn't matter, we generate this relationship where your partial differential of m over y at constant x equals to the partial differential of n over x at constant y. All right, that's how we get here. So far, so good? So let's apply it to one of our equations and see what does that lead to us. So this is where we derive our Maxwell relations. So getting ready. We're using the Euler's reciprocity relations to do it. So what do we have? We have my du as a function of s and v equals to TdS minus PdV. That's up there. That's one of my fundamental 6. And what we know in the previous case is, well, we're saying we have a function of z as a function of x and y. I'm just going to keep it here for your reference. So in here, what is my m? My m is my t. My x is my s. My n, big N, is my negative p. And what is my y? Is my big V. All right. And in previous cases, we derived that the partial differential of m over y at constant x equals to the partial differential of n over x at constant y. So that's the Euler's reciprocity relation. Now plug in my new mn and xy from my Gibbs equation. What are we getting? We're getting a relationship so that dm, which is t, over y, which is v, at constant x, which is s, equals to negative dp over ds at constant d. Yes.
Can you like equate m to t and x to s just because like the same thing on that factor, use a function of s?
Right, so we get this one coming from the original idea of impartial differential equation, or when you're taking second differential equations. It doesn't matter which one you take it first. That's how we get to this one. All right, and from here, we're just using the Euler's reciprocity relations into our Gibbs equations to derive this partial differential equations, or the relationship between these partial differential equations. Doing fine? I'm just gonna write this on the board, and then let's do it one more time together. And again, don't try to remember them, like knowing where they come from, knowing how to derive them. It's way more important than memorization of these relations. Let's do it one more time, okay? So this is what we have. I'm gonna copy paste our Euler's reciprocity relations on top. And then let's do it one more time. Let's just pick maybe dg. All right, so we have dg as a function of p and t equals to vdp minus sdt. All right, so in here, what do we have? We can write my m equals to v, x equals to p, big N equals to negative s, and y equals to t. Right, so using the Euler's reciprocity relations, we're getting my dm, which is dv, over dy, which is dt, at constant x, which is p, equals to dn, which is d negative s, over dx, which is dp, at constant y, which is t. Wait, did I get it wrong? I think I got it wrong. It should be. Okay. So we have n over x at constant y. N over x at constant. Okay. All right. So far, so good. So doing the same thing for all four Gibbs equations. You can try it yourself, but eventually we'll get 4 of these partial differential equations. That's dt over dp at constant s equals to dv over ds at constant p, ds over dv at constant t equals to dp over dt at constant d, ds over dp at constant t equals to negative dv over dt at constant p. So now thinking about why do we care? Why are we using these things? Remember, in thermodynamics, we have all these thermodynamic state functions whose changes will affect the macroscopic properties of my system, and we care about them, right? So we want to know, like, how does these state functions change when we change like temperature, volume, or temperature, So that gives us information that we need. But in most cases, we cannot directly measure, like for example, change of entropy. So in this case, thinking about what we just derived, so by using the Maxwell relations, what we're getting is a relationship between, say, how does my entropy change with respect to pressure at constant temperature. That is going to directly equal to how does your volume change with respect to temperature at constant pressure. All right, so this is something experimentally you can measure. And because of these relations that we're building here, we now have a way to say describe how does entropy change with respect to pressure. All right. How are we feeling so far? It's a lot of derivation, but if you think about it, everything we're doing here, we're only using these 6 fundamental equations and calculus, and we get like the rest of the blackboard. And let's take it one more step, right? Now we have these relationships. We have all these like tools in our boxes. What's the next step? Now, in previous cases, we were always talking about how to calculate the change of internal energy, the change of enthalpy, the change of entropy, or Gibbs free energy when your temperature, volume, and pressure changes, right? So the next question comes is how can we solve for these general rules that describe the dependence of state functions U, H, S, and G on temperature, pressure, and volume? And I should also add it. All right. We will be using the volume dependence of internal energy as an example. Volume and temperature dependence of internal energy. So what are we asking effectively? We're talking about the volume dependence of your internal energy. So the other way to put it is we're trying to solve for a general expression of how does your internal energy change with respect to volume at constant temperature. Because your internal energy in nature is a function of temperature and entropy. But in this case, let's just thinking about the change with respect to volume by keeping entropy or temperature unchanged. Now in here, where do we get started? We start from du equals to TdS minus PdV. Right, that's our first law and second law of thermodynamics. Now, in this case, I'm just moving my dV to the left, or divide dV on both ends of the equation. So du divided by dV, that gives me temperature times ds over dV minus pressure. All right. And then apply this constant temperature condition in there. So again, we know that internal energy is a function of temperature and volume. Now, when we're saying it's at constant temperature, I'm just putting my 2 normal differentials back into my partial differentials by adding my du over dV at constant T equals to temperature times ds over dV at constant T, and pressure stays as it is. And now we're facing some of the terms that we don't know how to solve, or we don't know how to experimentally measure. Because keep in mind, we're trying to come up with an expression that experimentally you can somehow measure it. So this is a hint of saying like maybe we should be using our Maxwell's relations. So survey the term, what do we have? We're looking for ds over dV at constant T, and that equals to my dP over dt at constant V. All right. And what does my equation become? Now my equation thus becomes my du over dv at constant T equals to temperature times dp over dt at constant V minus P. So this is already something we can solve for, but if we want to further simplify it into the coefficient that we predefined, now this coefficient, this will equal to my dp over dt at constant V equals to my alpha over chi. I think we did that derivation in one of the previous worksheets, but if you're wondering, it's the same as your alpha equals to 1 over V dv over dt at constant P, negative 1 over V dv over dp at constant T, and use the cyclic chain rule to get to the dp over dt at constant V. So what we're getting at the end is my du over dv at constant T equals to temperature times your alpha over chi minus pressure. Or that's the volume dependence of your internal energy. And it's always nice to do a quick sanity check. Like, for example, for ideal gases, what is something we know about ideal gases? We know that the internal energy of an ideal gas is only dependent on temperature, right? So from here, if we're applying that knowledge and say, okay, now let's test whether or not this derivation is correct. Now, what do we know? We know that for ideal gases, we have PV equals to nRT. So if we're looking at partial differential of P over T at constant V, what does that give us? Well, so my pressure equals to nRT over V at constant V. This differential equation is nR over V. So far, so good. And plugging to that equation, we get it to be du over dv at constant T equals to, well, temperature times nR over V minus P, and this equals to P for my ideal gases, so that equals to 0. And we're happy, because for ideal gases, we're expecting the internal energy to be not dependent on volume. Yes?
I remember reading in the book that there was a proof that all ideal gases must be perfect gases. Is this the proof?
No. So ideal gas and perfect gas are effectively the same thing. The textbook just like to use, the textbook just used two different terms out of nowhere. This is not the proof. This is just to demonstrate what we're getting here from the thermodynamic relations fits our expectation if we use ideal gas as a special case. All right. And let's see. Now, what about temperature? How does your internal energy change with respect to temperature? Well, temperature dependence of internal energy. So you can think about, okay, so we're writing internal energy change with respect to temperature while I want to keep my volume unchanged. So what is it? That's just my CV. Right, so CV is already something you can experimentally measure. So we're good, we're happy. So expressing the dependency of these state functions on your temperature, pressure, and volume, that's our ultimate goal. And now thinking about what else? What else do we know? Now start from here. What if we want to calculate delta U? Right, so what you're doing is you're taking the integration at normal, certain conditions and solve for delta U from here. All right, so using the same logic, we have the rest of the relationships that hopefully you can derive it yourself. Let's think about these things. For your temperature and pressure dependence of your enthalpy, now the first one, this one is pretty straightforward. You have enthalpy dependence over temperature, constant pressure, that's just your CP. And what about this one? So this one will do the same kind of derivation. Remember, in everything in here, we're not specifying them to be ideal gases. The equation of state is part of the information buried in your alpha and chi in these expressions. All right, so you might want to try it yourself and see like whether or not you know how to derive these expressions for temperature pressure dependence of enthalpy, temperature pressure dependence of entropy, temperature pressure dependence of Gibbs free energy. Okay, so we have 5 minutes. I'll take any questions you may have. Like the whole goal of today is trying to link everything we discussed before together, right? Remember, we start from our 6 fundamental thermodynamic equations. Like the first one includes both the first and second law of thermodynamics, and then these are just definitions of your enthalpy, Helmholtz energy, Gibbs free energy. And then we have CV and CP, right? We start by giving my heat capacity a different expression, and we'll use that in this case. For example, when we're talking about the entropy's dependence on temperature at constant pressure, that's just CP over T. That's part of this relation here, all right? And then next up, from here, we derived our set of Gibbs equation, which basically is saying, can you express your Gibbs free energy, Helmholtz energy, enthalpy in the format of these TdS plus VdP negative S dt minus PdV, this kind of format. In this process, we're using our first law and second law of thermodynamics and some calculus. And then from there, we end up getting the partial differential equations by writing out the total differential of my state functions. And at the end, we use the Euler's reciprocity relations to generate these relationships. All right, and keep in mind from here, we can then start to write the temperature and pressure dependence, temperature and volume dependence of these state functions with respect to changes of temperature, pressure, and volume. And things we can measure, like what are the things we can measure? Well, temperature, volume, pressure, heat capacities, Joy coefficient, Joule-Thomson coefficient, alpha, and chi. These are the things we can measure. Like in everything in this lecture, we're not specifying the equation of state. We're not specifying ideal gases. But once we get, like say, for example, the dependency, like the volume dependence of internal energy here, then you can start to use your equation of state. That's where your equation of state comes to play. For ideal gases, you have one set of volume dependence of internal energy. But imagine now I replace my ideal gas with, say, a liquid, right? When you have that incremental equation, when you have a different equation of state, then obviously this volume dependence of internal energy will become a different expression. All right, so the equation of state and thermodynamic relations are two sets of things that are orthogonal to each other. The equation of state is something you measure, and the thermodynamic relations gives you relationship between my thermodynamic state functions. And I hope today's lecture is going to be a whole like connecting the dots lecture of like, okay, so why do we care about thermodynamics? After all, thermodynamics, we use calculus, we use these thermodynamic terms and definitions as a tool so that we can measure things and that you don't have a thermometer, you don't have a physical way to measure it. You can translate it into something you can physically measure. So that's the whole point. And that's the beauty of thermodynamics. Doing good? Okay, any questions before we move on? Yes?
This is kind of like a practical question, but all these equations assume that we're only doing closed reversible PV work in like a closed system, right?
So right now, we're always following this equation, right? So we always start from our 6 fundamental equations. So if this one is not true, if it's not closed, reversible PV work only, well, then this one is not true. Then everything else is not. So later on, we'll move from equilibrium and start to talk about what if we don't have equilibrium anymore. Like how do we describe material equilibrium and talking about the concept of chemical and chemical potential. But for now, these are true for your equilibrium systems. And now it's a good point for you to start creating your own equation sheet, like knowing what to put on your equation sheet and knowing like where they come from. It's a total fair question if I ask you to derive like one of these Maxwell relations, right? So, okay, and that's everything from me. And I'll see you next, well, I'll see you 2 days later.
But it's